Hi everyone, I hope everyone is excited. I welcome you to join us to chapter 1 Leaping into Kubernetes. I am Astos, a lead platform engineer here at GreatFit, and with me I have another speaker, Gagan, with me. Through the entire series, we will be talking about core concepts of Kubernetes, why it is important to use Kubernetes as well for a day-to-day development and for deployment perspective as well. So hold up your horses and let's get started and dive into KubeVerse. At any time, please feel free to pause the video and rewatch it again if you feel like you are missing out. Right now, we are all set. Let's dive into the core of the Kubernetes. To really understand how it worked, its magic, we need to look at its high level architecture. And don't worry, we will break it down simply. At the very heart of Kubernetes, you have what's called a cluster. Think of the cluster as the entire operational unit, the foundation unit where everything happens. Now, within this cluster, there are two main parts. First up, we have the control plane, which you can think of as a API server, but it also includes other components as well. This is essentially the brain of the operation. Its main job is to manage the cluster and all workloads running within it. It's the decision maker keeping everything in check. Then we have the data plane, also known as worker nodes. If the control plane is the brain and data plane is the actual work gets done, those worker nodes are responsible for executing the workloads. That means they are the one running your containers. This is where your application live and operate. So in a nutshell, the control plane manage the cluster and the data plane executes from the control plane. These two components work together seamlessly to make up Kubernetes cluster. As we move forward, we will explore each of these in more detail. And remember, this is all part of our journey. Look at the Kubernetes control plane. Imagine our Kubernetes system as a busy shipping operation. The control plane is the captain's bridge or the port's command center. It manages everything and keeps the whole operation in a consistent state. On the bridge, we have few key officers. First, the API server. This is your ship's radio room or port's main office. All communication and commands for our container fleet go through here. It's the central hub for instructions. Next, the control manager. Think of this as the enforcer of the shipping plan. The, they constantly check if what we want our containers to be doing matches what's actually happening. If there's a difference, they work to correct it and get things back on track. Then the scheduler. This is our export load master. When new container our application arrive, the scheduler decides which ship or node it is best to put them on, making sure resources are used wisely. And finally, etcd. This is the ship's official logbook or the port's central ledger. It securely stores all the vital information about our ship containers and their current status. It's the single source of truth. So that's the control plane in a nutshell. API server for communication, control manager our plan enforcer for execution, scheduler for placement, and etcd for record keeping. Together they form a commanding crew to ensure our shipping operation is done wisely. Let's look at the data plane. This is simply where your application actually runs. Think of the data plane as each individual ship in your fleet. These are your worker nodes. Their main job is running your application, which are the containers of a cargo on these ships. Every zip or worker node in the data plane has three key parts. First, the kubelet. This is like the captain of each zip. It takes order from the main command zip and makes sure the application containers on each zip are running properly. Next, kube proxy. Think of this as zip's signal officer. It handles all the network connection for the apps, making sure they talk to each other and the outside world, and helps balancing the traffic. And finally, the container runtime, like Docker engine. So this is the engine of the zip. It's the container runtime that actually runs your containerized application. No engine, no movement for your apps. So the data plane is your fleet of ships. Each has captain, the kubelet, managing the app, a proxy signal officer for networking, and a container runtime and engine to run them. This is where your application live and work. Architecture. On the left is the control plane, our main command center. This is where decisions are made by components like etcd, the control manager, and the Kube API server, which is like our central communication tower. The green lines show the API server talking to our worker nodes on the right. These worker nodes are our individual ships in the fleet and they do the actual work. Each ship worker node has a kubelet, container runtime, kube proxy. A kubelet, as we know, is the captain of the ship taking orders from the main commander ship. Container runtime, the ship's engine running apps. Kube proxy, the ship's signal officer for networking. And what are these ships carrying? Pods. Think of a pod like a pea in a pod, and inside that pea pod, you have one or more peas. Those are our actual application containers running. This is where your actual container uh, contains running apps and code that runs. The control plane directs the worker node to execute the running of your application. The applications are running on a pod inside a container. So what we have in this architecture as a whole is that command and execution working together to deliver your apps that are running. Slide, we will talk about introduction to Minikube. But before diving into Minikube, let's know what Minikube does. So it provides a full Kubernetes architecture where you can develop or test something on your own computer. That's where Minikube comes in. Think of Minikube as a personal compact Kubernetes setup. You see, it's designed to be lightweight, which means that it's not doesn't have a massive installation process. It's ideal for running on a laptop for development and testing purposes without needing a whole server farm. It provides a local Kubernetes environment that runs on your machine. So you will get a real Kubernetes experience, just scaled down version. It also provides a simulation uh, which mimics the production Kubernetes cluster but on your local machine, which is fantastic for trying out things before you deploy to a bigger live environment. And it has cross-platform compatibility. That means that it will run on various operating systems like Windows, Mac OS, and Linux. Minikube is a super handy tool for anyone who wants to get hands-on with Kubernetes locally. It's your personal Kubernetes playground. Let's move on setting up our environment that is on Minikube. Now let's check if Docker is installed on our system or not. So we use docker version command to check if Docker is installed or not. So let's use systemctl command to check the status of the Docker. Perfect. It looks like our Docker daemon is running on the system. So I suggest you to install Minikube. So since my system has already Minikube installed, we will use Minikube version to check. Next, we will use Minikube status command to see if Minikube cluster is running or not. Now we will starting our local Kubernetes cluster using Minikube. We use Minikube start command. It may take few minutes to spin up your local Minikube cluster. Let's check the Minikube status again to see if our Minikube cluster is running or not. So it's all the things are running here. So we will be allocating a custom resource allocation for our Minikube with different profile name using hyphen profile option. This will create a separate cluster name Minikube conference. I already have a running cluster, so I won't be doing that now, but just to show you how it's done. I will cancel the command for now. You can view all your profile with Minikube profile list command. As you can see, my current profile is default one. You can pause the video here to look at the output. See what's going on. To interact with the Kubernetes, we will need kubectl command. This command will show the version that have been installed on your local machine. Now let's see how we can manage Kubernetes context. To know about how to manage context on Kubernetes cluster. So if you are working with multiple Kubernetes cluster, maybe one for development, one for staging, and one for production. Contexts are how you tell kubectl, our command line tool, which cluster you want to talk to. Think of a context as a shortcut that stores the cluster, user, and namespace you are currently targeting to. Here are some key commands you can use with the context. To get the available context, use kubectl config get context command. This simply lists all the different cluster setup you have configured. To switch to a different context or cluster, use kubectl config use context name. This changes which cluster you command will apply to. To view cluster details, use kubectl cluster info, which shows you the address of the control plane for your current context. It's a quick way to see where you are pointed to. And to set a specific context, use kubectl config set context command. With the cluster and the user details, you define a new context or modify an existing one. Managing context is crucially for efficient working with one or more Kubernetes cluster. It ensures your command goes to the right place. Talk about exploring Kubernetes resources. So resources as in like object in the Kubernetes cluster like pods. Let's go with number one, listing all API resources. So you can do that with kubectl API resource command, which will show you all types of resources available in a cluster. Next, we have get resources details, where you can get a blueprint of a specific resource type like such as pod or deployment. For example, you can use kubectl explain pod, which gives you the blueprint for the pod, same for the deployments or the services. These commands let you quickly see what you can use and how to use it, meaning that you don't have to go over the documentation entirely. With using this kubectl explain command, you can have a glance at what your resource types needs or what specific you need for the deployment. Let's zoom in. One of the most fundamental building blocks in Kubernetes, which is pod. A pod is the smallest and simplest unit you work within Kubernetes. You don't run containers directly on their own, you run them inside pods. A pod can contain one or more containers. There are your actual application running. Think of a pod like a pea in a pod and the containers are the piece inside. As you can see in the diagram on the right, all the containers within the same pod share network resources like the IP addresses shown, and also share storage resources like the external volume. This makes it easy for tightly coupled containers to communicate and share data within them. To create a pod, first you define the pod configuration in a YAML manifest file. This is like writing a blueprint for a pod, specifying what it should look like. In that YAML file, you will specify the container image for your application or any port that it needs, environment variable, and other settings. Then you will use kubectl apply-app-pod.yaml, the YAML file which you created in the Kubernetes, to tell how to create a pod according to your blueprint. You see, pods are the basic unit to run your application in Kubernetes cluster, providing a shared environment for one or more container. They are essential to run your application code. So you have your pod which runs your application. But what if one pod fails? Or what if you need more of them to handle more users? That's where replica sets come in. A replica set is a Kubernetes controller that makes sure a specified number of identical pod replicas are running at all times. As you can see in the diagram left, if this replicas set says replicas 3, it will always try to keep 3 identical pods running. It's mainly used by a high level of object control called deployments to maintain its desired number of pods. Why is this useful? It enables horizontal scaling, meaning you can easily increase or decrease the number of pods running for your application to match the demand of the users or the incoming traffic. And it maintains pod availability and reliability. If a pod dies, the replica set automatically creates a new one to replace it. Think of it like a self-healing mechanism for your application instances. So replica sets are all about ensuring you have the right number of active pods for your application, providing stability and scalability. Now let's talk about deployments. If replica set ensure you have the right number of pods, deployments are what you typically use to manage the entire lifecycle of those pods in a much more powerful way. A deployment is a Kubernetes resource that manages the lifecycle of your pod. This includes creating them, updating them, and even reverting them. It lets you define the desired state for your pod, like how many you want and which version of your application they should run. As the diagram shows, a deployment often uses replica sets under the hood to make sure your pods are running as a specified number. Most importantly, deployment automate critical operations like scaling up your application or down, performing rolling updates to a newer version without downtime, and crucially handling rollback, which means allowing you to easily revert to a previous stable version if an update causes problems. So when you need to release new versions of your application, update configuration, or ensure you can quickly recover from a bad release, deployments are your go-to resource. They provide control, automation, and safety for your application updates. Next, we will creating pod and deployment using YAML manifest file. We will be creating pod manifest file using vim command. So let's have a look at how pod definition looks like. You can pause the video here to look at the pod definition file. Now, what's important here is the API version, that is v1 for the pod. Next is kind, which is a key here and its value is pod. Next, we have metadata. For metadata, we will need a name and the namespace. The namespace here is demo, then the name of the pod is demo pod. These sections contain identifying information about the pod, not its actual content. Think of it like label or tags. Next, we have spec section. In this section, we define container, the name of the container, the image it needs to pull for running the application, and also the ports. Which is 80 for the image nginx. Now let's save this manifest file. Let's try to apply this YAML file to our Kubernetes cluster using the command kubectl apply -f the pod YAML file. Oops, it looks like we have an error. It says that the demo namespace is not found. Now, let's create our namespace called demo. So take the namespace as an isolated environment where you deploy our application into. We create namespace using kubectl create ns command. So looks like our namespace has been created. Now we will list the namespace using kubectl get ns command. So see, demo namespace has been created just now. Now we will use kubectl apply -f pod.yaml file again to see if the pod has been created. It shows the pod has been created here. So for listing the pod, we use kubectl get pod command. Oops, looks like there is no pod running on the default namespace. So let's switch the namespace to the demo and let's see if the pod is running. So as you can remember that in the manifest file, we have a section in the metadata called namespace. If you don't mention any namespace, a pod will be created in the default namespace. We will use kubectl describe pod with pod name to see the more information of the pod. Here we have container name called demo container. The container image is using nginx image. We can see its current condition status that is running, and we can see the events of the pod. Let's clear the screen now. So we have successfully created our pod. Now let's move on to the deployment. So now we will use vim command to create deployment. Let's have a look at deployment manifest file. This is the content of the deployment manifest file. Here the kind is deployment. Here we are creating a name called demo app under namespace called demo. This deployment will maintain two sets of replica of the pod. If one pod dies, the deployment will automatically create another to replace it, ensuring we always have two running instances of the pod. Under spec section there is section called selector, and under selector we have called match labels where the app value which will look for the pods that have specific label, in this case app demo. This selector must match the labels defined in the pod template below. In the container section, we are using image nginx. The name of the container here is demo container. The container port is 80, which is the default port of the nginx. Now let's save this deployment manifest file as a whole. Let's apply the manifest file using kubectl apply -f deployment.yaml file. Perfect, our deployment object has been created. Let's verify if our deployment object has been created or not using kubectl get deployment inside demo namespace. As you can see, we have 2 by 2 replica set of the deployment. Let's also check if the pod has been created in the same demo namespace or not. Here we can see there are two deployment pods we have just applied. Now to get the detailed information about the deployment, we can use the command kubectl get deployment demo app in the demo namespace with option -o wide, which will show the detailed output where you can see the container name, selector used, image used in the deployment. If you want to retrieve the manifest of the deployment demo app from the demo namespace, you can use kubectl get deployment demo -app -n demo -o YAML. This YAML includes all the configurations like metadata, labels, replica count, selectors, image used, and the container specs. To view the recent events in your Kubernetes cluster, such as pod creation, scheduling, image pooling, failed mounts, restart, and more, we can use kubectl get events. This is a powerful command for debugging and understanding what's happening under the hood in your Kubernetes cluster. It helps you answer questions like why my pod are stuck, did the image fail to pull, is there a permission or resource issue. So to recap, we have walked through pod and deployment, covering how to manage them.
Hi, it's me, Gagan. For the rest of the session, I will be switching over. So far, we have talked about deployments, which are great for stateless applications where any pods can handle any request. But what about applications that do care about their state, like databases? For those, we use a stateful set. A stateful set is specifically designed for managing the life cycle of stateful pods. Think about a database cluster, maybe a primary and a couple of replicas. Each of these database instances is stateful. It has unique data and a specific role. A stateful set ensures that each of these pods gets a stable, unique network identity, like a fixed host name. For example, DB0 and DB1 and its own persistent storage. As you see in the diagram, this pod is linked to its own distinct volume. This means if DB0 restarts, it comes back as DB0 and connects to the same storage, keeping its data. Key features of stateful sets include ordered deployment, scaling, and termination. For databases, this is critical. You might want to bring up the primary first DB01, then the first replica DB1, and so on. Stateful sets manage this order. This makes them ideal for stateful applications like databases, message queues, or any system where each instance has a persistent identity and data. It preserves the identity of files across restarts, ensuring reliable connection and data integrity. So, when your application needs each instance to be unique, remember its name and hold onto its data consistency, like the individual server in the database cluster. Stateful set is the Kubernetes tool for the job. So we have our pods running our applications, but pods can come and go. They can be restarted, scale up or down, and their IP addresses can change. So how do you reliably connect to our application? That's where a service comes in. Service is essentially an abstraction for networking in Kubernetes. It provides a stable, single endpoint, like a fixed IP address and port, for accessing a group of application pods. As you see in the diagram, traffic comes to a service, and the service then intelligently distributes the traffic to one of the underlying pods. This enables communication between the different sets of pods within your cluster and also allows external clients to reach your application without needing to know the individual IP addresses of each pod. There are a few main types of services. First one is cluster IP. This is the default service. It gives your service an internal IP address. It's only reachable within the cluster and it is good for backend services. Second one is node port. This exposes your service on a static port on each of your node's IP address. It is useful for making your service accessible externally for development or testing. Third one is load balancer. This is typically used with cloud providers. It creates an external load balancer in the cloud that directs traffic to your service, making your application accessible from the internet. In simple terms, a service acts like a stable front door or a well-known address for your application, no matter what's happening with the pods behind it. Let's do hands-on lab of service. We'll focus on understanding Kubernetes services. Let's start by basic service manifest file. Okay, let's break this down. We have defined kind service. This tells Kubernetes we are defining a service object. Here we are naming our service demo service and placing it within our existing demo namespace. Under selector section, it tells the service which faults to route traffic to specifically faults labeled with app demo in the demo namespace. To understand this better, let's look at the associated deployment file. As you can see, the pods created by this deployment carry the label app demo. This is what allows the service to discover and connect to them. So the service doesn't connect to the deployment directly. Instead, it uses the label to find the pods created by the deployment. Let's go back to our service. Under port section, we have protocol TCP. This defines the transport protocol, and TCP is the default and most common choice for HTTP traffic. Here we have port 80 on which the service is exported within the cluster. Under the target port, this is the port on the target ports which is defined in deployment file where the traffic should be forwarded. So traffic hitting the service on port 80 will be directed to port 80 of the selected ports. Finally, we define the service type as cluster IP. Cluster IP is actually the default type. It gives the service an internal IP address, making it reachable only within the Kubernetes cluster. This is perfect for backend services or when you are enabling internal communication between microservices. Now let's apply our manifest file of service to the cluster with command kubectl apply-f service.ml. Excellent! Our demo service is now created. To verify this and see its details, we'll use kubectl get service -n demo. Here we have our demo service of type cluster IP and it has been assigned an internal cluster IP and exposing port 80. For a more detailed view, we can use describe command as kubectl describe service demo service -n demo. If you look at the endpoints line, you will see the IP addresses of the pods selected by our app demo selector. Kubernetes continuously monitor pods matching this selector and update these endpoints automatically. If we need to access our application from our local machine, we can forward a local port on our machine to port on the service within the cluster. Here we forwarded the 80 port of the service to 32,100 port in the local machine. The ampersand at the end run this port forward in the background. If we want to remove these services we have created, we can delete the service by the command kubectl delete service demo service -n demo. Let's see the service has been deleted or not. Well, the service has been deleted. So in this session, we have seen how to define a cluster IP service to provide a stable internal endpoint for our application pods, how the selector links service to the pods, and how port forwarding allows us to access these internal services from our local machine for development. Let's talk about how we can organize our Kubernetes cluster, especially as it grows. This brings up the concept of namespaces. As you can see in the diagram, a Kubernetes cluster can be thought of as a large environment. Namespaces act as a logical partition of the cluster resources. Think of them like separate virtual clusters within your single physical cluster. They provide a crucial mechanism for isolating environments. For example, you might have a development namespace staging namespace, and a production namespace. This ensures that resources and configuration for one environment don't accidentally interfere with another. Furthermore, namespaces are incredibly helpful for managing large-scale deployments by providing resource segmentation. In a large organization with many teams or projects, each team can have its own namespace. This helps prevent naming conflicts, allow for easier management of permissions, and provides a clearer overview of who owns what resources within the cluster. In essence, namespaces help keep your Kubernetes cluster organized, secure, and manageable, especially as your application and team scale. Alright, everyone, it's time for a quick knowledge check. We have covered some fundamental concepts, and now it's your turn to test your understanding with a quick survey question. Take a look at the screen. The question is, what is the smallest unit of Kubernetes? Your options are A. Pod, B. Node, C. Deployment, and D. Service. Please pause the video here and take a moment to think about your answer. I'll give you a few moments to consider your answer. Alright, have you made your choice? Let's reveal the answer and see if you got it right. And the correct answer is a pod. A pod is indeed the smallest, most basic deployable unit in the Kubernetes, representing a single instance of running process in your cluster. Congratulations to you who got it right. Moving on, let's discuss how we handle configuration in our Kubernetes applications. This is where config maps comes into play. A config map is a Kubernetes object used to store non-sensitive data as key value pairs or files. As you can see in the diagram, a config map can be accessed by multiple pods, providing them with necessary configuration. They are incredibly useful for application configuration, such as storing URLs for external services, database connection string, or file path within your application. Instead of hard-coding these values directly into your application's image, you can externalize them. The main benefit here is that a config map decouples configuration from your application code. This means your application image remains generic and you can apply different configuration to it depending on the environment or specific deployment needs. Crucially, config maps can be updated without redeploying pods. If you need to change the configuration value, you can update the config map and the pods consuming it will often pick up the changes without needing to be restarted, making updates much more efficient. Config maps provide a flexible and efficient way to manage configuration data from your applications in Kubernetes. Let's have a look at config map. We can use config map in two different ways, as environment variables and as mounted files inside containers. Let's create a config map which is used as environment variable. Here you can see the configuration of config map. We are defining a Kubernetes object of kind config map. Inside the data section, we have two key value pairs. App mode is set to development and log level is set to debug. These are configuration values that application can access at the runtime. Let's save this configuration and apply this config map using kubectl apply-f envconfig.ml. Here we created a config map which we'll be using to mount as an environment variable. We can see the config map envconfig with two data entries which was just created. Next, let's create a deployment that uses this config map to inject values as environment variable. Here is the deployment manifest file. Though we have already discussed the deployment, let's only see the env section of the deployment manifest file. We are defining two environment variables here. App underscore mode pulls its value from the app underscore mode key in the envconfig config map. Log underscore label does the same for the log underscore label key. Let's save this deployment file and apply it and see how the values of the config map is used in the pod. Here the deployment is created. Let's check the pods with command kubectl get pod. Here we can see one pod is running. Let's enter into this pod and see the configuration. Copy the pod name. We can enter the pod with command kubectl exec-it, paste the pod name, space, double dash and giving the cell name as such. Now we enter the pod. We already mentioned that we are going to use the config map to mount as an environment variable. Let's print the environment mounted in the cell. Here we can see log underscore label variable is mounted as an environment variable. Also, we can see app underscore mode is also mounted. In this way, we can use the config map to mount as an environment variable. Next, we will create another config map that contains a sample Nginx configuration file. This one will be mounted as a file inside the container. Here we are creating the config map, volume config, and we are defining the data in the key value pairs. Here the key is config-file.conf, which represents a file name when this config map is mounted as volume. The value we can see in multi-line string and it's the actual content of the configuration file. Let's save this file and create a config map with this configuration. Using the command kubectl-f volume-config.yaml. Now let's verify the config map we just created with the command kubectl get config map. Here we can see the config map volume config which we just created. Now let's use this config map in the deployment and mount it as a volume mount. We have already created a deployment file to demonstrate the environment variable mount. Let me add some configuration where the config map we just created will be used as a volume mount. Here we go. I have added this section in the previous manifest file. Under the volume mount section, I have defined a volume mount name config-volume and container mount path as /etc/nginx/conf.d. And under the volume, I created a volume name config-volume which sources its content from the config map volume-config. Let's save the deployment file and apply the manifest file. Here we are using a config map as an environment variable and the volume mount in the same deployment file. And here the deployment is created. Now let's check the pod with the command kubectl get pod. Copy the pod name. Later we use this pod name to enter into the pod. Let's enter into the pod that is just created with command kubectl exec-i and paste the name of the pod we just copied, double dash and provide a cell. Here we provide the cell as such. Here we are inside the container. We have already verified the config map is mounted as an environment variable, and again let's see the environment variables. We can see both the variables with their value are present. Now let's check whether the volume is mounted or not. We have specified the volume mount at /etc slash nginx slash conf.d. Here we can see the file config.file.conf. Let's check the content of the file with command cat config-file.conf. It's the same data which we have created in the config map. In this demo, we explored how to use a config map within a pod in two different ways, by mounting it as environment variables and by using it as a volume to inject configuration files. If your application requires simple key value pairs at runtime, environment variable mounts are a great option. On the other hand, if your application needs full configuration files, volume mounts let you inject those files directly into the container. Depending on your use case, you can choose the most suitable method or even combine both as we did here. While config maps are great for non-sensitive configuration, what about sensitive information like passwords, API keys, or certificate? For that, Kubernetes provide secrets. As the name suggests, secrets are designed to store sensitive data like password, tokens, and certificates. Unlike config maps, where data is stored in plain text, data within a secret is base64 encoded and can be encrypted at rest within your cluster, adding a layer of security. The primary purpose of secrets is to provide sensitive information from being exposed in plain text within your pod definition or other Kubernetes resources. This significantly improves the security posture of your applications. Similar to config maps, pods can assume secrets either as environment variable or as mounted files. This allows your applications to securely access the credentials they need without hardcoding them or exposing them in a version control. In summary, when dealing with any sensitive data for your Kubernetes application, always reach for secrets to ensure that this information is handled securely within your cluster. Let's look at Kubernetes secrets, a native way to store and manage sensitive data like password, tokens, access keys, and credentials. We will walk through how to use secrets in two powerful ways inside your pod, as an environment variable and as a volume mounted files. Let's walk through both methods step by step. First, let's create a secret and use it as an environment variable. Here is the manifest file. Here we are creating a Kubernetes secret resource of kind secret. We named this secret as app-secret. The type is set to opaque, which is the default and is used for key value pairs. Here we define two secrets under the data section, db underscore username and db underscore password. The value of the secrets are here stored in the base64 encoded formats. For more detail on the secret, please refer the Kubernetes official documentation. There you can find the way of creating secrets. Let's save this configuration file and apply to create a secret. With command kubectl apply -f secret.ml. Let's verify the secret has been created or not with command kubectl get secrets. Perfect. Our secret app secret has been created. We can see the secret with two data and a secret type as opaque. Now we are going to mount this secret app secret as an environment variable. For this, let's create a deployment file to mount this secret as an environment variable. Here we are mounting the secret in the container named demo-container. In the env section, we are referencing a secret we just created and mount it in the pod. Here we are creating the environment variable named db underscore username and mounting the value of the key db underscore username of the secret app secret. Similarly, we are creating another environment variable db underscore password in the pod and storing the value of the key db underscore password of the secret app secret. Here we have defined the two variables in the pod. If there are multiple variables you need to mount, you can use multiple variables as per your requirements. Also, you can mount multiple secrets in the same pod. Now let's save our deployment configuration file and apply this with command kubectl apply-f deployment.ml. Here we can see the deployment demo-app has been created. To list down the pod, let's use command kubectl get pod. Here we can see one of our pod is running. Copy the pod name and we'll use it later to enter into the pod. Let's enter into this pod and see the environment variables are mounted or not. Here we are inside the pod. Now let's print the mounted variables with printenv command. Here we can see two of our variable is mounted with the value of the secrets we have created, db underscore username and db underscore password. This variable will be mounted as individual files inside the container at the mounted directory. Now let's mount this secret as volume. Let me use the same deployment file and add the configuration for mounting the secret as a volume. Under the volume mount sections of a container, you can see we are referencing the secret we have created earlier named app secret and named the volume mount as secret volume and mounting it in the path /etc/secret inside the pod. Inside the container, all the secret keys will be mounted as individual files under /etc/secret. Let's save this configuration and apply the deployment manifest file with command kubectl apply-f deployment.ml. Well, the deployment is created. Let's list the pod created with kubectl get pod command. Here we can see one pod is running. Let's copy the pod name. We will enter into this pod and see the secret has been mounted or not. To enter into the pod, we will use command kubectl exec-it and paste the name of the pod we just copied and give the cell as bas. We have already verified the secrets are mounted as environment variable. Again, let's see the environment variables with printenv command. We can see both the variables db underscore password and db underscore username are present with their value. Now let's check whether the volume is mounted or not. As I already mentioned, the secret will be mounted as individual files. Let's see the secrets are mounted or not in the directory. Here we can see two different files with the key name of the secrets. Let's verify the value of the secrets which are created as individual files, whether it will match the value we inject in the data section of the secrets or not. Let's view the content of db underscore password file. Well, it's the same base64 decoded content we inject in the data of the secrets. Similarly, let's view the content of the db underscore username file. Again, we can see the same base64 decoded content of the key db underscore username we inject in the data of the secret. In this demo, we saw two ways to use Kubernetes secrets in a pod, as environment variables for simple key value access and as volume for injecting the files. You can choose either method or both based on your application needs. So far, we have talked about pods, deployments, and how they manage our application instances. But what happens to our application's data when a pod is restarted, deleted, or moved to another node? This is where persistent volumes become essential. A persistent volume, or PV, is a Kubernetes abstraction for persistent storage, unlike local storage on node, which is ephemeral and disappears when a pod dies. A persistent volume provides a way to store application data that persists beyond the pod restart or deletion. Think of a persistent volume as a piece of storage in your cluster, like a network attached storage or a cloud provider disk. As you see in the diagram, the cluster has various storage options. A persistent volume claim or PVC is how a pod, or rather an application running in a pod, requests a specific amount and type of persistent storage from the cluster. It's like asking for a specific size of a drive. This separation of persistent volumes and persistent volume claims allows administrator to provision storage independently of how application consume it. The application simply requests what it needs via PVC, and Kubernetes handle the binding to an available PV, often facilitated by a storage class which define different types of storage. Beyond persistence, persistent volume also enables sharing data between multiple pods or applications. For instance, if you have multiple instances of an application or different applications that need to access the same dataset, a persistent volume can provide that shared access. In a sense, persistent volumes ensures that your valuable application data remains safe and accessible, even as your pod comes and go, providing the necessary durability for stateful application in Kubernetes. Let's look at another important resources in the Kubernetes, persistent volume. Let's look at the manifest file of the persistent volume. Let's break this down. Here we define the Kubernetes objects of kind persistent volume. Under metadata section, we name the persistent volume as mypv. Moving to the specs section, we define the storage capacity of 1 GB. We define access mode as read-write once. Access mode defines how the volume can be mounted. Read-write once means it can be mounted as read-write by one node at a time. We define persistent volume reclaim policy set to retain, which means that the volume won't be deleted automatically after release, preserving the data for manual cleanup. We named storage class name as standard, which helps Kubernetes match persistent volume claims to the right persistent volume. Finally, host path specifies the actual path of the node's file system where this storage resides. In this case, we define /mnt/data. Now let's save this configuration and apply the manifest file with command kubectl apply-nav pv.ml. Let's verify the persistent volume creation with command kubectl get pv. Here we can see the details of persistent volume. The capacity is 1 GB and reclaim policy as written, and the status of the persistent volume is available. It means that the storage resource is free and ready to be used by the pod once a claim is made. The persistent volume only represents the physical storage in the cluster. To request this storage, we use persistent volume claim. Let's see the manifest file of persistent volume claim to claim the storage request. For the persistent volume claim, we define the kind as persistent volume claim. Under the metadata section, we name this persistent volume claim as mypvc. Under the spec section, we define the storage request of 1 GB storage with read-write once access mode. We define storage class name as a standard. This tells Kubernetes what type of storage the claim needs, and it will match with the persistent volume that has the same storage class. Let's save this configuration file and apply this manifest file with command kubectl apply-nav pvc.ml. Let's see the detail of persistent volume claim we just created with command kubectl get pvc. Here we can see the persistent volume claim mypvc is created, and it is bound with the volume mypv which we created earlier. Let's again see the details of persistent volume. Here we can see the status of the persistent volume is bound. Previously, we can see that it was available because no claim has requested this volume. Now the volume is claimed by the persistent volume claim mypvc. Now let's see how our application actually uses this storage we defined with the persistent volume and persistent volume claim. For this, we define deployment file as shown here. Here we named our deployment as demo app. Inside the container block, we use volume mounts to mount the volume my storage into the path /usr/share/nginx/html. This is the default location where the nginx serves static files, so now anything written to the persistent volume will be visible to the web server, and it will persist even if the pod is deleted or recreated. We define a volume name my storage, and instead of specifying host path, we use persistent volume claim and point to the claim named mypvc. Now let's apply this configuration and see how the persistent volume works in the pod. Well, deployment with persistent volume is created. Now let's list the pod and enter into the pod to see the persistent volume mounts. Let's copy the pod name and we'll be entering into this pod with command kubectl exec-it and paste the pod and provide a cell name. Here we provide cell assets. Let's go to the directory of the pod which we have mounted with the persistent volume. Now we are adding some files in the minikube cluster and see whether the file will be mounted here or not. For this, let's enter into the minikube cluster and go to the directory /mnt, which is the persistent volume mount directory. Here we create a test file, test.txt file with content hi from Minikube conference. Now let's enter into the pod and verify that the volume is mounted in the pod or not. Let's go to the mounted directory in the pod /usr /share /nginx /html which we have mounted. Here we can see the file test.txt is mounted in the pod. Also, let's verify the content of the pod with command cat file name. And yes, as the same content we created. So that's how the persistent volumes and persistent volume claims work together in Kubernetes to provide durable, reliable storage for your application. By abstracting the storage and connecting it through the claims, Kubernetes ensures your data can persist seamlessly across the pod, restart, or rescheduling. Now, let's look at the comprehensive diagram that ties together all the basic Kubernetes objects we have discussed for continued deployment. As you can see in the slide, everything operates within the Kubernetes cluster. To keep things organized, we use namespaces to logically partition our cluster resources, providing isolation for different environments or teams. At the heart of managing our applications, we have deployment. The deployment primary role is to manage replicas, ensuring that a desired number of identical application instances are always running. These replicas are responsible for creating and managing our individual pods. For external access and stable communication, our service acts as a consistent front door to our pods, intelligently routing traffic to the healthy instances managed by the deployment and its replicas. Inside our pods, our applications need configuration and data. This is where config maps comes in, providing non-sensitive configuration data while secrets securely handle sensitive information like passwords and API keys. Both config maps and secrets can be consumed by pods as environment variables or mounted files. Finally, for applications that require persistent storage, volumes are attached to the pods, ensuring that data outlives the pods themselves. This allows our applications to maintain their state even if pods are restarted or rescheduled. This diagram beautifully illustrates how all the fundamental Kubernetes objects works in to provide a robust, scalable, and manageable environment for deploying and running your containerized applications. Now, let's talk about a very powerful and often overlooked feature that can save you a lot of headache: validating changes without the consequences. When you are applying changes to a Kubernetes cluster, especially in production environments, you want to be absolutely sure that your ML manifests are correct and will behave as expected. This is where the dry run option comes into play. The dry run flag allows you to simulate the application of a change without actually modifying any resources in your cluster. It's like a test run that tells you if your command would succeed and what changes it would make without actually committing them. This is incredibly valuable for debugging and ensuring correctness. Let's look at some basic commands using dry run. First, we can see on the slide, we have kubectl apply-app deployment.yaml dry run flag with server. When you use dry run flag with server, Kubernetes API server performs a full validation of your manifest, including admission controllers, just as if it were a real request. It tells you if the object would be created or updated successfully on the server side without persisting it to etcd. This is the most accurate way to validate your ML against the current state and policies of your cluster. Next, we have similar dry run command with client options. With dry run command with client option, the validation happens purely on your local machine using the kubectl client. This is faster as it doesn't involve a round trip to the API server, but it won't cause server-side validation error or admission controller issues. It is good for quick syntax checks. Similarly, we have this imperative command which also does the same things like dry run flag with client option. By incorporating dry run into your workflow, you can confidently validate your Kubernetes manifest and commands, significantly reducing the risk of unintended changes or errors in your live cluster. As you work with Kubernetes, you will often need to understand the structure and available fields for various Kubernetes resources. This is where the kubectl explain command becomes incredibly useful, allowing you to understand Kubernetes resources at a glance. The kubectl explain command provides detailed documentation for any Kubernetes resource directly from your terminal. It's an invaluable tool for quickly looking up what fields are available for a given object, these data types, and a brief description of their purpose. Let's take an example kubectl explain pod. When you run this command, it will output information similar to what you see on the slide. It tells you the kind, what is pod, and the version number, which is V1 in this case. It also provides a concise description. Pod is a collection of containers that can run on the host. Most importantly, it lists the top-level fields available for a pod. For instance, you will see metadata, which refers to a standard object's metadata, and spec, which defines the desired behavior of a pod. You can then drill down into this field by running kubectl explain pod.metadata or kubectl explain pod.spec to explore these subfields. This command is your go-to reference when you are writing ML manifest or just trying to understand the capabilities and configuration options of any Kubernetes object. It helps you build correct and effective configurations without constantly referring to external documentation. Next, let's look at how we can securely interact with Kubernetes API from our local machines, especially when you don't have direct external access to the API server. This is where kubectl proxy comes in. The kubectl proxy command starts a local HTTP proxy to the Kubernetes API server. Essentially, it creates a secure tunnel from your local machine to the API server inside your cluster. This command is incredibly useful because it enables secure access to the cluster resource and the Kubernetes API from your local machine without requiring direct cluster access or complex firewall configurations. You can then access the Kubernetes API through your local proxy address like http localhost 1001. This is particularly beneficial for development and debugging. For instance, you can use it to access the Kubernetes dashboard or to directly query API endpoints from your browser or other tools, all while maintaining a secure connection to your cluster. To achieve this, simply run kubectl proxy command. Once executed, this command will keep running in your terminal, forwarding requests from your local machine to Kubernetes API server. You can then open a new terminal or use your browser to interact with the cluster via proxy address. So, whenever you need a convenient and secure way to route traffic to your Kubernetes API from your local environment, kubectl proxy is the command you are looking for. Now, let's explore another useful command for directly interacting with applications running inside your cluster, kubectl port forward, which bridges local systems to Kubernetes. This command allows you to forward a pod on your local machine to a pod on a pod or service within your Kubernetes cluster. This creates a direct, secure connection by passing any network policies or external exposure. This is particularly useful for accessing applications running inside the cluster without exposing them publicly. For example, if you are developing an application and want to test it directly from your local browser or development environment, but the application is running in a pod that's not exposed externally, Port Forward is your solution. It's also invaluable for debugging. You can forward a pod to a specific pod to inspect its log, connect a debugger, or interact with the internal service, all without making that service publicly accessible. In summary, kubectl port forward is your go-to commands for securely and temporarily accessing internal applications or services within your Kubernetes cluster directly from your local orchestration, making development and debugging much more efficient. Now, let's talk about comparing Kubernetes states. We have kubectl diff command for this. It is useful for comparing the states. It shows the differences between the live state of a resource in the cluster and a desired state defined in your manifest before applying changes. This command helps to prevent unwanted modifications. By reviewing the diff output, you can catch accidental changes, misconfigurations, or unintended deletion before they impact your live environment.
Now let's have a look at Kubernetes documentation. We go to kubernetes.io for documentation. Here you can find concepts and also the documentation required for the object like uh, cluster, container, workload. Let's have a look at workload on pods. This is the pod definition. Let's search for API documentation. Let's have a declarative API validation documentation overview. Let's search for API reference documentation. This is mostly used for developing manifest file, is asset key and value. Similar for the pods. Like we have create operation, where can we create, what can we do with the pod. Similarly for the service, let's have a look at an example. This is how our service manifest looks like, as we have covered before. What are the settings and the parameters we can supply. Similar for the config map. Let's see how config map can be created, right? It's REST API HTTP code. Similar for the secret. So you can have these all documentation on the API reference, documented references on the Kubernetes official documentation. So in this way, you can browse any Kubernetes object and it's find out its parameters required for it to run.
So far, we have learned how to manage individual Kubernetes resources. But what if you have a complex application with many interconnected components, like a database, a backend service, and a frontend, all needing their own deployments, services, config maps, and so on? Manually managing all these YAML files can become cumbersome. This is where Helm and Helm charts comes to rescue. Think of Helm as a Kubernetes package manager for easy application deployment and management. Just like you use package managers on your operating system to install software, Helm helps you install, upgrade, and manage complex applications on Kubernetes. The core concept in Helm is Helm chart. A Helm chart is a packaged set of Kubernetes YAML manifest for deploying resources like deployments, services, and config maps. It bundles all the necessary Kubernetes resources for an application into a single versionable package. Let's look at the key components of Helm chart. First, you have the chart itself, which is package containing all the Kubernetes manifest. This includes templates for your deployments, services, and other resources. Crucially, every chart comes with a values.yaml file. This values.yaml file is the configuration file for customizing your deployments. Instead of directly editing the YAML templates within the chart, you modify the values.yaml file to provide specific configuration for your environments such as image versions, replica counts, or external URLs. This allows you to reuse the same chart across different environments or for different purposes by simply changing the values. Helm charts provide a standardized, repeatable, and efficient way to define, install, and manage even the more complex applications on Kubernetes, making application lifecycle management significantly easier. Now, we understand what Helm and Helm charts are. Let's summarize the key benefits they bring to manage applications in Kubernetes. First and foremost, Helm provides simplified deployment and management. Instead of dealing with numerous individual YAML files, you can deploy and manage an entire application stack with a single Helm command. This significantly reduces complexity and the potential for errors. Next, we gain excellent version control and rollbacks. Helm charts are versioned, allowing you to track changes to your application deployments over time. If a new deployment introduces issues, you can easily roll back to a previous stable version of your application with a simple command ensuring reliability. Helm charts offer reusable and customizable templates. As we discussed with the values.yaml file, you can define a standard chart for your application and then customize it for different environments like development, staging, production, or for different clients simply by changing the values. This promotes consistency and reduces duplication. They also facilitate easier application updates. When you need to update your application, whether it's a new image version or a configuration change, Helm handles the upgrade process gracefully. It manages the rolling updates of your Kubernetes resources, minimizing downtime and ensuring a smooth transition. Finally, Helm excels at dependency management. Complex applications often rely on other services like databases or MySQL. Helm allows you to define these dependencies within your chart, ensuring that all necessary components are deployed and configured correctly together. This simplifies the deployment of multi-service applications. Helm transfers the way we deploy and manage applications on Kubernetes, making it more efficient, reliable, and scalable. Now that we have covered the benefits of Helm charts, let's look at some of the commonly used Helm commands that you will interact with on a daily basis to manage your applications. First, to get started with charts from public or private repositories, you will use Helm repo add command. This command adds a Helm chart repository to your local Helm configuration, allowing you to fetch and install charts from it. Once you have a repository added, the most fundamental command is helm install. This command is used to deploy a new instance of a chart into your Kubernetes cluster. You provide a unique release name for your deployment, specify the chart name you want to install, and optionally use the namespace where it should be deployed. To see what you have deployed, you can use helm list command. This command lists all the release deployed in your cluster, giving you an overview of your helm managed applications. For detailed information about a specific release, helm status is your go-to command. It shows the status of a named release, including its revision, last deployed time, and the resources it has deployed. When you need to update an existing application, you will use helm upgrade command. This command upgrades a release to a new version of a chart or applies new configuration values to an existing release, performing a rolling update of your application. Now, if you want to remove an application deployed with Helm, you use Helm uninstall command. This command uninstalls a release from your cluster, cleaning up all the Kubernetes resources associated with that release. These commands form the core of managing your applications with Helm, providing a powerful and streamlined workflow for Kubernetes deployments.
Now let's have a look at Helm documentation. We go to helm.sh, right? We have this quick guide where you can find info on how to install Helm chart, basically entire life cycle of Helm chart. So we do repo update for added Helm repo. We check the uninstall and status of the Helm chart. Have a look at Helm chart documentation site. To install any Helm chart, we go to artifacthub.io website. Let's search for WordPress chart, right? So we have the install instruction here. Let's scroll down. Let's see the configuration it requires for the WordPress installation on Kubernetes cluster. We have default values where we can manipulate values. We can even compare the comparison with the versions. Let's exit the comparison now. Let's see at the instruction how we can install the chart itself for the WordPress. So we are gonna demonstrate a bonus video using K9s. So let's add a Helm chart repo for WordPress that we showed earlier. Let's follow the instruction. It will take a couple of minutes to spin in your Minikube cluster or even a Kubernetes cluster like AKS, EKS on the AWS GKS. So we see this instruction, how can we put forward for the deployment we have done via Hemchart for the WordPress. Let's use K9s command. Let's have a glance at how it looks like. So you see it will display the Minikube cluster and the user and also the deployment. Let's search for a pod. Let's see if pod is running or not. So you can see the pod. Let's look at the WordPress container. We can see these are the contents that has been inside WordPress pod. We can describe the pod itself. Let's search for config map. You can see the config map of the WordPress. Let's have a look at secrets for the WordPress. It is listing all the secrets in the Kubernetes cluster for the default namespace. You can view YAML format file as well for the secret. Let's have a look at service. The benefit of using K9 as CLI comparing it to kubectl is that it provides a ease to use what's happening and interact with the clusters object rather than having a full-blown command like kubectl git pods and all. So it is providing us the easy navigation. So let's have a log of the service. We press Alt and view the live log of the container associated with the service. Now next we will be forwarding our port to our local host. Here we do port forward using port forward, and we do shift F for forwarding to our local host. Let's have a look at context. So we have three contexts here. So context, at any time if you need help, you can see the help menu. For more ease navigation, I recommend you to go to the KN and SCLI documentation for interacting with the Kubernetes cluster. So this is a way that you can have to easy navigate without having full-blown command that helps you to save time rather than having fully typing the kubectl command for interacting with the Kubernetes objects. Let's scale a pod in a deployment. Let's delete it and see if our next pod is spinning in replacement for the pod that we have just deleted. Right, we can see the pod has been spinning. Let's have a look at the deployment. These are the deployments we have. Let's delete deployment, and let's also have a look at the events. This way you can have a more easy way to interact with the cluster objects as a whole. Well, that's it for us. Thank you for watching this video. This is just a starting video. There are several other paths that you can take. We will coming up with another chapter as well. So that's it from us. Thank you.